Thank you, Maxime, for the intro. It's great to be here finally. So let's dive into applied computational thinking. Computers, they have changed us in a true transhumanistic way. They're constantly questioning our relationship with nature, enriching all of our culture. So let's have a look at what makes us computational thinkers and how that applies to practices of today and tomorrow. Who am I? How did I get here? I did this school in Paris that was called Gobelin, where I worked with graphic designers on real-world projects, then learned the ropes of advertising at Unit 9, a production company, and then joined Viable, a small studio, design studio. More on that later. If I have to put labels on what I do, who I am, I'd say I'm a creative developer, so I use code as medium for creating something expressive rather than purely functional. So for instance, turning pixels into visually pleasing images. Also an amateur tennis player. Talk to me about Roger Federer after the talk if you want. I'm a computational designer, and for me computational design is system-centric design magnified by the use of computation. And I'm also a generative artist. So I'm going to go over the art practice, what is generative art, which medium I use, and the tools and techniques. But first of all, generative art, what is this? It's a very broad discipline associated with several terms: computer art, parametric art, algorithmic art, and let's just focus on the main characteristics here by giving a small definition. In generative art, we produce artworks by building very often rule-based systems and by delegating some parts of the decision-making to a computer. The result of generative art is oftentimes visual, but the outputs can be really diverse, so the art form is not really tied to a specific medium. And it emerged with computers in the 60s, and I'm quite fascinated by what people could already do at the time with much, much less computation power that we have nowadays. To give you an idea of that, I'll tell you the story of Manfred Mohr, a pioneer of digital art who narrated this story in an interview. He was getting well established in Paris in 1969 as a traditional art painter, and he decided to move on to explore the possibilities of computer art. And he joined a new program in the Université of Vincennes, close from here, that was called Art et Informatique, or Informatique. And one day on TV, he saw a small meteorology program, and they were using a plotter. So a plotter, for those of you who don't know, it's the bottom right picture here. It's a mechanical arm, very often 2 dimensions, with a pen attached to it, so you can draw stuff on paper programmatically. And the next day after he saw that program, he walked into the computer room, because you could do that in 1969 apparently, and asked the operators what he needed to do to have access to the plotter and the computers there. So they told him, go see our directors. He met him, told him, you can't really just do that, you need approval from the Ministry of Transportation. He came back to the university, asked the director of the university to write a letter for him, which he did, saying that Manfred needed the computers to do his research, etc. 2 weeks later, got an interview with the director of Météorologie Nationale. And that was really the lucky break for him, because this person told him, I wanted to be an artist too when I was young. And he gave him 5 minutes of computer time every day at night. And these are the 5 minutes that really he started the next 11 years of research in digital art from him, and allowed him to do some of the pieces that you can see on the right. So you see, big struggles to get just a tiny bit of computer access. At the heart of every generative art pieces, there's a form of algorithmic computation happening to generate colors, create geometries, add textures, compose an image, or drive a simulation. Simple example of that would be a quad-tree subdivision algorithm where you start with a simple square, divide it along an axis, then you roll a dice. If the value is, let's say, above 4, you cut it in two, and you do that a certain amount of time with a few more conditions, and you obtain a quad-tree-like structure. The algorithm is one thing, but the generative part of generative art also comes from the use of randomness, like the rolling of dice in the previous example. That gives the possibility of having different structures in the final outcome. I say randomness, but it's actually pseudo-randomness because true randomness doesn't really exist in computer worlds or real world. That's another philosophical question. And so for that, we use pseudo-random number generators. I will say it only once. That have three main qualities. They are able to simulate randomness. So we call a function usually that return a number. We call it again. The number are going to look different, random. These generators are cyclical, but they do it over a very long period. So humanly, it's quite impossible to keep calling it and go back to the beginning. And they are also deterministic. If I start at one point in the cycle, as for randomness, I will get always the same values. That's very useful for artists who want to control a bit randomness. Even though we can control it, it also brings a sort of feedback loop between artist and machine where we see some behavior emerging and we get surprised by it and react to it. A domain that really managed to harness the potential of pseudo-randomness is blockchains. And the idea here is to associate networks code on a blockchain in a block and allow people to mint iterations of the artwork. So each artwork is given a hash from the blockchain, a random sequence of numbers that you can use to feed to a pseudo-random number generator. There you go, can't say it. So people here, they're more buying into a system of what an artwork can do more than just a picture, a JPEG of a monkey. And for me, that gives greater significance to the algorithms used to generate the artwork and the artwork itself. And for us artists, it's also a big shift here conceptually that we called long-form generative art, where we go from devising an algorithm, pressing refresh in our browsers, try to select the best outputs that will look good on Instagram, wherever. We go from that to carefully craft a system that can generate pertinent outputs with every seed. And to conclude on this small dive into generative art, here is the final set of all the 512 mint iterations of window that were minted on the Tezos blockchain, grouped by similarities thanks to a Disney algorithm. That's for generative art. And my work oftentimes involves the use of data and data visualization. The connotation of the discipline might be a bit dry sometimes, but when I think about it, I don't really think of bar charts. I just think basically at the graphical representation of information, abstracted or not. Let's talk about it a bit more later. And finally, tools and techniques. I mainly use web technologies, Canvas 2D, JavaScript, and the graphics API, WebGL, and the upcoming WebGPU in a similar way that some game developers might be doing stuff. And that's on top of making art. All these interests, they push me to release open source modules and work on side projects. And I don't need to introduce this project because Maxime did the intro already. But this is the Harpa concert hall. The interesting constraint here was that we had to work with very little resolution. The whole building, it's something like 77 by 15 pixel in total, because each LED is a pixel. So I did this representation of the northern lights, and there was a small booth where people passing by could press on a button and shoot stars. So all the previous topics and more, they require computational thinking. I'll first have a look at the term's history and definition, then show how it applies to today and what's its place in tomorrow's society. So from what I understand, it's a term that's mainly been used in academic communities and also as a buzzword in the US to promote the use of computers earlier in school. The idea or its premises, they are around since the 50s, and they've been around under different names: algorithmizing, algorithmic thinking, combinatorial thinking. And if some of these ideas share the concept of formulating problems in order to convert some input into outputs, they weren't necessarily thinking in terms of computation. You could formulate problems in philosophical or mathematical manner that is not translatable to machine code. Whatever the naming, these ideas, they tend to emphasize the value of coding concepts and more generally the use of computers as a mental tool for understanding all kinds of problems. It crystallized with the creation of the Logo programming language by Fertzek, Papert, and Solomon. It's a programming language and a computational environment that could stimulate and promote the way children think and solve problems by means of activities that direct, encourage, and strengthen the knowledge learning. So a sort of learning by doing with computers approach. One point I want to stress is that it's a way of thinking that shouldn't be thought as the only way. It's complementary to a lot of other ways of thinking. In 2006, the term has been revised by Janet Wing, a professor of computer science. She said computational thinking is the thought processes involved in formulating problems and their solutions so that the solutions are represented in a form that can be effectively carried out by an information processing agent. Give myself a breather and for you time to read it again if you want. She does try to make it a bit more clear by defining some points. She says that computational thinking is conceptualizing, not programming. Thinking like a computer scientist means more than being able to program a computer. It requires thinking at multiple levels of abstraction. She also says it's a way that humans, not computers, think. She's not trying to equate another. And if computer science foundation is in mathematics and computational thinking is also building systems that interact with the real world, that's closer to engineering. Here we kind of have a reconciliation of the craftsman, or here the new craftsman, and the thinker. And she states that it's ideas, not artifacts. It's not just the software and hardware artifacts that we produce that are physically present in our lives around here. It's all the computational concepts we use to approach and solve problems, manage our daily lives, communicate and interact with other people. She also says it's for everyone, everywhere. I'll probably be a bit more nuanced here. But she also proposed a set of operational and functional definitions to reframe computational thinking. It's quite a long list, so I'm not asking you to think about it too much. Just try to point out if you can see a bit of yourself in it. So if you reformulate a problem into a solvable one by using reduction, transformation, or simulation, if you think recursively, if you understand parallel processing, if you recognize both pros and cons of aliasing, if if you're able to judge a program for its aesthetic and not just its functionality, then you are a computational thinker. If you use abstraction and decomposition, if you understand the separation of concerns, are able to choose appropriate representation to make a problem tractable, if you're able to use, safely modify a large system without necessarily understanding all of its parts, if you modularize, prefetch, cache in anticipation of future uses, you act as a computational thinker. Lastly, if you think in terms of prevention, protection, and recovery from the worst-case scenarios, if you use heuristic reasoning to discover a solution, plan, learn, schedule, even when you don't know what the future holds, search, and more search, using massive amounts of data to speed up computation, are able to make trade-off between time and space, and processing power and storage capacity, you are a computational thinker. If this sounds familiar to some of you, it's probably because as programmers, you have naturally learned to do that and developed some of these skills. So programmers, computer scientists, are obviously most prone to function as computational thinkers, as already computer literate. And although Janet Wing advocates for everyone to be versed in computational thinking, not just people related to computational areas, I don't think it's 100% realistic, simply because of the ever-changing nature and diversity of both hardware and software. But if you look at history and the current use of computers across so many disciplines, you're reminded that technology defines human as much as human defines technology. And that's what J. David Bolter did in 1982, some time ago, by expanding the era-defining terms of classical man of antiquity and the enlightened modern man to what he called Turing's man. And to define Turing's man, his premise was that humans and technology need to be analyzed together. It makes sense to examine Plato and pottery together to understand the Greek world, Descartes and the mechanical clock to understand 17th and 18th century Europe. If you define technology as the controlled application of power to manipulate the environment, we need to understand each civilization through its set of materials, techniques, devices, which provides both physical means of life, but also shape cultural outlook, moving some technologies from luxury to necessity. Yeah, and our human tendencies of exploring, manipulating the physical world, it led over the course of history to a deeper appreciation of the world's resources and made humans re-examine their relationships with nature. If you think of the Middle Ages water wheel that harnessed natural water currents and shifted the work from something more manual, slaves and animals, to something more mechanical. If you think of the Industrial Revolution's steam engine for transforming another natural resource, coal, for increasing productivity. And now if you think of the computer, the information age's computer, you see that it also reshaped the nature-culture relationship by giving a new definition of human as information processor and of nature as information to be processed. It's such a defining technology partly because it embodies very human characteristic. If you think of computer memory, random access memory, it's more similar to the associative memory that humans have, more similar than what we had before computers to keep memory, which is book, which is a bit more frozen and linear. The infinity representation, because finite representation of numbers is how computers work. That brings up a philosophical question that I said before, and also the symbolic representation of the computer that helped already develop new theories of linguistics and create new models of cognition. So as a whole, the computer is the triumph of logic and embodies the human capacity of rational thinking. So defining ourselves as information processor, as biological machines, that also gives us means to pursue the quest of AGI, artificial general intelligence, in the long line of humans attempting to recreate themselves. So, understanding how technology changes humans and vice versa, and how computers and AI are more powerful than any other technology before, we have the responsibility of guiding it in the right direction. For that, we need education programs to follow and some foundational knowledge to be built. Part of this is going to be understanding computers and humans' limits. Think of it, at their core, CPUs are just that. They are discrete. Everything is broken down to bits. When you sample audio, it's just broken down to discrete values. They are finite, as I said before. An algorithm, it's a step-by-step procedure, has a beginning and an end, and conceptually, computers only navigate between idle and executing states. They are also conventional, just as decimal is usually humans' way of counting binaries computers, and the bit in itself doesn't hold much connotation, contrary to ancient Greece, where 2 and 3 had specific meanings. And they are isolated. Outside its transistor, the world is chaos. If in the past humans were computers, our physiology is just limited compared to what computers can do. So taking some ideas from John Maeda, How to Speak Machine, let's have a look at what computers are good at. They run loops and use recursion. They don't need sleep, only power. They are unambiguous. They think in a coldly precise manner with formal symbols, without connotation and metaphors. And they're also very good at conventional networking that allows them to operate at greater scale, at an exponential scale, while we humans are more operating on linear scales. And while we're good at identifying patterns in data, we struggle to do it at scale with large datasets because of cognitive noise. These small videos, Power of 10, is a good way to show the scale we operate on and how hard it is to sometimes grasp the scale computers operate on. Understanding the qualities of computation will help people harness that power and navigate an ever more computational society. For people, that can take very tangible forms, help them make better decisions when it comes to finding a flat or deciding to try a new restaurant instead of the familiar one. If you want answers to that, check the book, Algorithms to Live By. For democracies, human rights, and individual liberties to survive, I think computational thinking is kind of a necessity. Schools need to build generation of aware citizens, not just consumers. People who understand what scrolling on TikTok means for their digital footprint. People who understand the privacy concern of and controlling end-to-end encryption, and very often under the pretense of protecting children, and the technical nonsense that it is. Just quote Meredith Whittaker, encryption is either broken for everyone or it works for everyone. There's no way to create a safe backdoor. So if computational thinking is impacting the way we live, it also impacts the way we work, and the leaders of tomorrow, for me, they are algorithmic leaders or they are not really leading. These leaders will not only work, they will design work and be good at automating and elevating both their products and teams or their countries and citizens. But these algorithmic leaders also need to be taught ethics and humility, as the power of this technology is greater than most historical advances so far. And this problematic, we see them raised more and more since large language models have broken into the mainstream in the past few months, the ChatGPT and such. If they appear conversational and their associative thinking is closer to how human brains works, they are still computational. there will be a need to evaluate how they change the way we live, we work, and communicate. And for that reason, humanists need to understand them and play with them to test their limits. So for all these reasons, I think individuals and societies would benefit from more computer literacy and computational thinking. All right. Problem that you have when you do what I did, which is think about a way of thinking, you start to get a bit disconnected from your reality. So I want to put a bit more tangible words on it and see how this knowledge applies. So let's try to sum it up and see how it applies to my way of working at different levels. My work is a process of transformation of an input into an output. I always remember the first class of chemistry where we learned, I think in English it's called the law of conservation of mass. Nothing gets lost, nothing gets translated, everything is transformed. And going back to computational thinking definition, the schema is simple. It's some kind of problem that is tackled to attain a goal, an output making clearer and clearer the black box, problem solving with computational help. And as a generative and data art practitioner, I build systems, and this is the global process I always come back to at some point while creating parametric systems. This schema here, parameters, abstraction, representation, and expression, that naturally raises more questions, such as how much abstraction is too much? What if I don't know all the parameters? Are some parameters more meaningful than others? Or even more concretely, what is the social, economical, cultural context of my expression? Am I using bias tool? Am I inclusive enough in my expression? But this representation is a bit too linear. In reality, it's a bit more of a loop between abstraction, automation, and analysis. It's a loop that circles until we believe the outcome is strong enough or until the deadline hits us sometimes, and we feel okay to break the loop. And this teamed up relationship, computer-human, it's continuously opening new worlds of possibilities, and that also applies for me in art making. So let's just have a look at another piece of mine called Sandal. It's a data art pieces that live on the Tezos blockchain, still long-form generative art. And the first step in the loop was analysis. So I reread Le Rouge et le Noir de Stendhal. It's a staple of the French literature. And I got to understand a bit more the historical context of France at the time. With that, I had enough information to abstract the components that I deemed interesting and start revealing the data by doing a sentiment analysis on it. So finding out if each sentence is positive or positive sounding or negative sounding. And now I could convert all of this into a geometrical system informed by my personal Westerner experience, where, for instance, the positive sentence direct the baseline up from left to right. I could also give significance to the numbers of parallel lines, their angles, and the level of recursion to represent different things, such as the main character state of mind. And finally, taking advantage of the fact that I knew it would live on the blockchain, each iteration would be different, I added more tension by adding these dots and triangles that will end up always at different places depending on the minted iteration to represent the conflicted society and the complication it had on the main character's patience. You could stop there, call it a day, but it's always interesting to go back to analysis and try to discover new meaning. It's an important part of enriching the artwork. And so I went out, find new shapes, find out what works, what doesn't, and adjusted some parameters. I also went back to abstraction at some point because I wanted to give this, yellowish old book covers with this wrinkly texture. So I added dithering to the final artwork. Not sure you can see it on this projector, but trust me. And I also worked on different color palettes to evoke certain eras. The last step of the process is seeing it as a whole, being a long-form generative art piece, and try to get a good balance between coherence and uniqueness. So I generated a lot of this, and this is the final set of all the minted iteration. So that's the process I use both in my personal work and also as part of my studio variable. What we do is we work with brands, research groups, organizations on new ways of experiencing data and understanding complex systems with generative strategies, computational design, machine learning algorithm, data visualization. We combine all of that with human sensitivity. How we do it? We do it with data visualization, research and development, generative and data art, and by creating bespoke design tools. Our process, we use data as a medium. I think you get the idea from now. What is data? I didn't answer this question yet. It's a set of organized qualitative and or quantitative variables. But for us, what it means is the medium, a medium that can be experienced and not just counted. I'll go with my favorite quote from Sherlock Holmes. It's a capital mistake to theorize before one has data. So our process is really starting with data, trying to unfold, understand the data, because we need to see the data, maybe in a more classical bar charty way. And from there, we apply the computational thinking process of building systems and destructuring them, and so forth. As I said before, generative art is not really tied to a single medium, so we use that to generate outputs that can live on mobile, on screen installation, on websites. I'll give you two examples of the kind of work that we do. The first one is inflows, outflows, which represents 10 million data points of immigration patterns between 2006 and 2014. We got this visualization, which is 3D, but a bit more classic and linear, and we converted it into data sculptures, living data sculptures, with different levels of readability. The left one is probably the most readable one, but they all can be experienced in different ways. Another project was the IBM Technology Garden, which is a good dream project for a tennis player, where at Wimbledon, we had the opportunity to work with IBM because they collect a bunch of data for every matches. And we transformed all this data into a digital garden of flowers that were on the booth, on site, and they were data-driven and opening more or less depending on the weather conditions, the cybersecurity attacks on the websites, this kind of stuff. And this is the most obvious and readable representation of a single game where each branch represents the final score of the game, 6-2, 6-4, 6-4, etc. Everything controlled by an iPad on site. So we're generally curious people, and a motto that resonates with us is, what I cannot create, I do not understand. So to understand ourselves and our job better, we created Nodes, which is an app. When you think about it, half of the human brain is devoted directly or indirectly to vision. So when you think of that, you start thinking that writing code in a classic text editor might be a bit limiting and distracting, and the solution would be providing another layer of visualization reduced to parameters and their relationships. So that's visual programming. It's been around for some time. So we were motivated to create nodes because we wanted to move from this kind of mental map to a visual map. We did it on the web because the web has a lot to offer, and all the tools at the time, we weren't cutting it. I'm going to go over the features of nodes just quickly so you get a bit of an idea of the context, and then I'll jump right into the demo. But what you need to understand, the core of it, it's a graph, the structure that is constituted of nodes that have parameters to link the nodes. Each node, it's a piece of code that can handle data flow and parameters. We have an editor to edit, navigate the graph, nothing fancy here, just undo, redo, etc. And as I said, each node, it's a piece of code because we have a programmer-first approach. It's not a no-code tool. And all of that is compiled on the fly in a browser in a simple live evaluation loop, so instant feedback. We have a potential to visualize the graph state. So for instance, seeing how much CPU, GPU is used. There's more potential here to do some different kind of visualization. And similar to the text editor, we also have comments and annotation that are either static or dynamic, which is great when you do 3D and computer graphics in real time. Sometimes you need to see what's happening, and it's good to have this feedback. Lastly, we have publishing and exporting capabilities, so we can share prototypes with clients very easily by publishing some of the parameters of the nodes. That's good for the clients, but also for creating small tools for other designers to use. It's good for screen-based installation where we have to tweak stuff quickly on the fly. But that was a pitch. Now let's have a look at the demo and see if I can make this work. So let's go up full screen. Can we turn the light a bit, please? Great, so we can see something. So the interface here is simple. On the left, we have the graph. Here we have a scene container where we're going to draw stuff, and we have an inspector that's going to be filled with nodes parameters. So to start with, I'm going to try to draw something. I created a context node, zooming, which is basically filling the space with the JavaScript canvas, WebGL1, actually WebGL2. You can see this is changing the size of the canvas here, and that's the first step to draw stuff. We have a bunch of convenient nodes that we often use, and the first one is going to be time. I'm going to need to keep track of the time, how all of that executes. And as I said, each node is a piece of code, so I can, in theory, edit it. I should have mirrored my screen to do that, but that's going to be fun. So speed, let's add some speed to these time nodes to keep track of time. So I created a port here that is called speed. That is a float value. And here in this loop, we have trigger. This is the part, the callback that is being called by the parent node. And I could multiply the time by speed, the port value. And now, if I exit the node here, I have this port added here for speed, and I can multiply this to make it go very fast into the future. It's good sometimes to see animations. So code, but now let's try to add stuff to this black canvas. For that, I'm going to need to have a scene. A scene has two outputs. The first one is to add stuff to the scene, and the second one is to render them. For rendering, I'm going to need a render engine. It is hard to see on this small screen. Okay. Nothing happening yet because I need to add entities and cameras to the scene to visualize. So in 3D world, we usually have lights and cameras. Camera. So this camera is added. I can check that it's working by changing the background color. Sorry if I blinded you. So everything is already rendered in the render engine. I'm not super interested about changing the background color, just the background color. So I'm gonna add a skybox to it, which is a basic sky. And I'm a bit lost in 3D space, so I'm gonna add some helpers, see where we are at with just a basic axis. Gonna make my camera draggable by changing this dropbox, and here, drop down, here we have the axis. I'm gonna add another thing, a grid, just to be sure we know where we are at. Yeah, okay, that's better. So with that, I can start adding some geometries, and for that I need a node called mesh. The default geometry of the mesh is a cube, but we can change it. These are a bunch of nodes that we are currently creating and trying to find a way to release to the public. But here I chose a torus. Good donut. And I can make it look a bit prettier. For that, I'm going to change that sky to an environment map. So we use these maps to automatically kind of create reflections. And I have already one here. So now the whole scene is going to be lit by this room here. That's already impacting the reflection of the torus. It's a bit distracting, so I will blur it, but the reflection will still be applied to the torus. Now, this torus, it's also a bit boring, so I'm gonna add material to it and try to get some space. A material that is gonna be made of a texture for the color, so we can change the color here by selecting textures. It's not super realistic, so I'm gonna add more texture to it to make it look more physically based, rendered. This is a normal map, which is gonna add a bit of bumps to the torus, to the surface, and finally I can also make it look half metallic, half rough, with a roughness map here. Voila. Roughness texture. That gives a bit more of a look to this torus. If I don't like the color, I can multiply the texture by this color and change it. Another interesting thing we can do with nodes is copy-paste between graphs, and for that I have the cheat code here where I can what's going on? I can try I will try in a moment to select all these nodes. No. And I can copy. Hopefully this worked. And paste everything here to connect it. Well, before connecting it, what I want to do is put some particles on the torus, so I need to connect the torus to all of that, to a particle system, and I think it's here, geometry, and this is a particle system, so I'm going to need to add a few globals to it, connect everything. Wow, it's hard to see. That. All right, so now I have my globals and I can connect my particle system here, and hopefully it works. There you go. So this is the particle system that comes from here. We have a reset button. I can go full screen and this button is going to be published, so I can show you where these voids, these bird-like particles, are starting from. Not lying, they are starting from the torus. There you go. So that's the demo. And I'm gonna leave you with a few takeaways. Take time to feedback and reflect on your practice. Embrace the computational thinking loop. Thank you, everyone. Questions? I don't know if we have time. Yeah. So I think the project started a bit before I joined Variables, and it was in 2017. So since then, it's an app that we published it. We made it public for everyone to use, but it's really the core of all of what we do. We use it on every project, and we keep improving it and building as we build projects, basically. Yeah. Cool. Right. Thank you, everyone.